Good evening to one and all present here. With great pride and immense pleasure, I welcome you all to the 5-day faculty program on innovative applications of mathematics in real-world challenges, organized by the Department of Mathematics, New Prince Shri Bhavani, Chennai. First of all, I would like to thank our management for encouraging us to conduct this type of event. Mathematics is not just about the numbers and equations. It is the language of logic, technology, and innovation. This FDP aims to bridge theoretical knowledge with practice in solving real-world challenges and also to create interest among the students. With utmost respect, I welcome our esteemed chief guest, honorable speakers, for all the 5 days. Director, principal, head of the department, faculty members, and all our dear enthusiastic participants. Just as every equation finds its balance in truth, may the blessings of the Almighty, clarity, and wisdom to our 5-day learning journey. Now, I invite our young and charming head of the Department of Science and Humanities, Dr. S. Sivagami, to present the felicitation address.
Good evening to one and all present here. Yes, ma'am. Good evening to everyone present here. It's with great joy and pride that I extend my warmest felicitation to the organizer, dignitaries, resource person, and participants of this 5 days International Faculty Development Program on innovative applications of mathematics in real-world challenges, organized by the Department of Mathematics, New Prince Shri Bhavani College of Engineering and Technology. My heartfelt appreciations go to Thiru K. Loganathan, founder and chairman, Thiru L. Naveen Prasad, vice chairman, for their visionary leadership and constant support in forecasting academic excellency. I would also like to felicitate Professor A. Swaminathan, Director, Dr. T. Saravanan, Principal, for their encouragement and guidance in organizing this event. A special appreciation goes to the organizing team, Dr. G. Pushpalakshmi, FDP Coordinator, Dr. Anita Florence Vinala, Co-Coordinator, and organizing committee members, Ms. Eldin Jiva, Ms. Geeta Ramani, Ms. Nandini, Dr. Subhatra, Mr. Kartigeyan, Dr. Saundra Pandian, Mr. Arpuda Jose. For their dedicated effort in successfully planning this international program, we are truly honored to have this as eminent resource person from across the global. Dr. Vijay Kumar, COE, Professor of Mathematics, GIET University, Odisha. Welcome you, sir. Dr. Joseph Milinsi, Senior Lecturer, Department of Mathematics, University of Rajni, Uganda. Dr. Mallikarjuna Rao, Head of the Department, Raghu Engineering College, Visakhapatnam. Dr. Karupaiya Kannappan, Assistant Professor, Government College of Engineering, Bodinayakanur. Dr. Shaila Manavalan, Professor, Houston University College, Texas. Your presence and knowledge sharing will undoubtedly inspire all participants and contribute greatly to the academic growth of our faculty and researchers. Once again, I extend my heartfelt congratulations to the Department of Mathematics and wish the FDP great success. Thank you all. Anita ma'am.
Thank you, ma'am, for your inspiring words. I now invite our program coordinator, Dr. Pushpalakshmi Gopalakrishnan, Assistant Professor, Department of Mathematics, to welcome the gathering and to introduce our today's chief guest.
Good evening to all. Good evening to all. Dr. P. Vijayakumar, COE, Professor of Mathematics, GIAT University, Odisha. Today's title, Recent Advances in Graph Labeling. Work experience, Dr. P. Vijayakumar is having 26 years of teaching experience as a lecturer, senior lecturer, assistant professor and professor at different engineering colleges and universities, and holding the position of controller of examinations in GIAT University from November 2019 to date. He is having a broad knowledge of organizing, managing and supporting the day-to-day activities required for running an educational institution. He talked with teaching all mathematics courses of undergraduate and postgraduate engineering students for different programs. In addition, he is carrying out research, supervising masters and doctoral students, produced 1 doctorate and 4 undergoing. Achievements and awards. He published more than 26 articles in reputed and in international journals. He presented his talk in more than 20 international seminars and conferences of various titles. Organized 3 national conferences and grants received from CSIR and TNSCST. Administrative responsibilities. He is flexible with strong team working skills, able to work individually or as part of a group. Now I over this session to our tireless, experienced academic administrator and dynamic Dr. P. Vijayakumar to deliver his presentation on recent advances in graph labeling. Welcome you, sir.
Thank you, madam. Thank you for a nice introduction.
Thank you, sir.
So let me share my screen.
Yes, sir. Welcome, sir.
Is my screen visible?
Yes, sir. Yes, sir, visible.
Just. Is my screen visible?
Yes, sir.
Okay. Good evening to one and all. I'm Dr. Vijayakumar, Professor and Controller of Examinations, GIAT University. I'm very happy to be part of this 5-day FTP. And research is a daily learning thing. And people, those who are doing research, should read every day and learn new things every day. Am I audible?
Yes,
Am I
sir.
audible to you?
Yes, sir. Audible,
Yes,
sir.
sir. Yes, sir. Audible, sir. Yes, sir.
Thank you. Thank you. So, let me give a brief introduction on graph labeling. And whatever I know, what little I know, let me share with you. And let me post some of the open problems also. So, in recent days, the recent research topics on graph theory. First is general graph theory, then algebraic graph theory, graph labeling, graph coloring, dominations in graph theory, chemical graph theory, fuzzy graph theory, spectral graph theory, stochastic graph theory, and so on. So these are the areas where you can concentrate. And I'm good at graph labeling. So let me give you a brief introduction and a little knowledge about graph labeling. Now, what is a graph labeling? Graph labeling is a function which assigns integers to vertices or edges, or both, subject to certain conditions. When the domain of the mapping is set of vertices, then the labeling is called vertex labeling. If the domain of mapping is set of edges, then the labeling is called edge labeling. If the domain of mapping is both vertices and edges, then the mapping is called a total labeling. Now, myself and my students are doing research only on duplicate graphs. This concept was introduced by Sampath Kumar, a professor of mathematics from Mysore University in the year 1973. And he derived some characteristics of duplicate graph. So first, let me tell you what is a duplicate graph. So for any graph G of V comma E, we can form or we can derive a duplicate graph. Let G of V comma E be a simple graph. A duplicate graph of G is denoted by dG, whose vertex set is V1 and whose edge set is E1. And V dash will be disjoint, and F is a bijective function. And for notation, for simplicity's sake, we take for every G in V, we write the image of or copy of G as G dash. And the edge set of the duplicate graph is obtained from the edges of the graph itself. So whenever YZ is an edge in the given graph G, then there exist two edges, YZ dash and Y dash Z in the duplicate graph. So here generally what we do is we take copies of each vertices of the given graph, and for every edge of the given graph there exist two edges. So let me explain this through an example. So here we take a path graph with three vertices and two edges. Now in duplicate graph, generally what we do, we take copies of this vertices. So for V1, we take V1 dash, for V2, we take V2 dash, and V3, we take V3 dash. So now corresponding to V1, V2, V3, we have V1 dash, V2 dash, and V3 dash. Now, according to the definition of duplicate graph, for this V1, V2, we must have two edges, V1, V2 dash, and V2, V1 dash, like this. And similarly, for the edge V2, V3, we must have a pair of edges, V2, V3 dash, and V3, V2 dash, and will be like this. So this is the duplicate graph of the given path graph. Now, this duplicate graph of path graph is disconnected. So in next few slides, I will be explaining, and I will convert this into a connected graph. So these are the results derived by Professor Sampath Kumar in his paper, which was published in 1973. So when G is a graph with a vertex at V, then the duplicate graph DG, in duplicate graph DG, no 2 points of V and V dash are adjacent. So that is, no 2 points of V will be connected and no 2 points of V dash will be connected. And if G has P points and Q edges and L loops, then the duplicate graph will have 2P vertices and 2Q plus L edges and no self loops. For each vertex A in the given graph V, the degree of A in the given graph G will be equal to degree of A in the duplicate graph and will be equal to degree of A dash in the duplicate graph. And these are the results derived by Professor Sampath Kumar. And for a connected graph G, duplicate graph is connected if and only if G contains an odd cycle. And duplicate graph of a graph G is twice or copy of the graph itself if and only if G has no odd cycle. And for this, we have two corollaries. For any graph G, duplicate graph is bipartite. And for a tree T, duplicate tree will be copy of the given tree. Then let me give you some graphs and their duplicate graphs, and some of them will be extended duplicate graphs. And I tell you why we extend the duplicate graph into an extended duplicate graph. Now here, let me tell you about ladder graph and its duplicate graph. So this ladder graph is a Cartesian product of two path graphs. So I am taking this ladder graph with the vertices G1, G2, G3, G4, G5, G6. And with reference to the definition given, I am constructing the duplicate graph of this ladder graph. Now let me explain only few edges. Now let me take the edge G1, G2. Now corresponding to this edge G1, G2, there must be two edges G1, G2 dash and G2, G1 dash. So here G1, G2 dash and G2, G1 dash. Similarly, for G1, G3, there must be two edges G1, G3 dash and G3, G1 dash. So G1, G3 dash and G3, G1 dash. Now, accordingly, we will complete this duplicate graph. Now, in a similar fashion, we will take triangular ladder graph and its duplicate graph. So the triangular ladder graph is obtained from the ladder graph by joining the diagonal vertices of the ladder. And here it is cycle graph and its corresponding duplicate graph. Sun graph is obtained from cycle graph by attaching a pendant edge to each of the vertices of the cycle. And the corresponding duplicate graph is drawn here. Now star graph. Now star graph is a complete bipartite graph K1M. And here, let me take the star graph S4, where this 4 represents the number of vertices. Now the corresponding duplicate graph. Now when you look at this duplicate graph, when you take the green color edges and red color edges, so it becomes two different graphs. So it is completely bipartite, and moreover, this is not connected. Generally, people, those who work on labeling of graphs, they consider only connected graphs. And there are few papers, few authors, they worked on disconnected graphs also. So now this is a duplicate graph and this is not a connected graph. So in order to make this a connected graph, we join G1 and G1 dash so that the duplicate graph becomes connected. We call this as extended duplicate graph of star graph. Similarly, bi-star graph. And these are all the basic graphs, so you may be knowing. So let me move on to the next step. And here also, the duplicate graph of bi-star graph will be disconnected. So in order to make it connected, we join G1, G1 dash. And you may ask a question, is it necessary to join only G1, G1 dash? The answer is no. You can join any two vertices with the original vertex and a copy of other vertex. So you can even join G2, G2 dash, G3, G3 dash, etc. But the thing is, when you join the vertices with more incident edges, then labeling will be simple. Then double star graph is obtained from star graph by adding a pendant edge to each of the vertices of the star graph. And here comes the path graph, as explained earlier, where in the second slide, I explained about only the duplicate graph. That graph was disconnected. Now, in order to make that duplicate graph connected, here I am joining V2, V2 dash. Here you can also join V1, V1 dash, but here the number of edges incident with V1 and V1 dash are only 1, whereas the number of edges incident with V2 and V2 dash are 2. It is having the maximum number, so I join V2 and V2 dash. Then comes comb graph. Comb graph is obtained from path graph by attaching a pendant edge to each of the vertices of the path. And here also the duplicate graph of comb graph will be a disconnected graph. So just in order to make it connected, I'm joining V1, V1 dash. And twig graph is again obtained from path graph by joining two pendant edges to the internal vertices. This V1, V8 are the extreme vertices, and this V2 and V5 are the internal vertices. So the twig is obtained from path again. And the duplicate graph of this is constructed, you can construct, and similarly the duplicate graph of twig will be disconnected. So again we will be joining V1, V1 dash. Now in general, let me give a broad classification of graph labeling. Graceful labeling, it was introduced by Rosa in 1960s. Then comes harmonious labeling, and Kahit introduced cordial labeling as a weaker version of both graceful and harmonious labeling. Then comes mean labeling, magic type labeling, anti-magic type labeling, radio labeling, and many more. And even within this, we have more than 70, 80 types of graph labeling. And now under graceful labeling, let me cover few types of labelings. One is graceful labeling, odd graceful labeling, even graceful labeling, odd even graceful labeling, 1 modulo 3 graceful labeling, Skolem graceful labeling, K graceful, KD graceful, and etc. And few more graceful labelings exist. Now, what is a graceful labeling? So as I told you in the beginning, graceful labeling, graph labeling is nothing but a function. So here this injective function H from set of vertices to 0, 1 to Q. It means the vertices of the graph are labeled with 0, 1, 2, 3 up to Q, where Q represents the number of edges of the graph. It's called a graceful labeling of the graph G of P comma Q if each edge Y, Z is assigned the label absolute value of H of Y minus H of Z, such that the resulting edge labels are distinct. So for simplicity's sake, I'm considering only star graph. So in the definition, it is told that the vertices of the graphs are labeled from 0, 1 to up to number of edges. So here we have 4 plus 4, 8, 8 plus 1, 9 edges are there. Therefore, the vertices of the given graph can be labeled using the integers from 0 to 9. So now here I have labeled G1 with 1, G2 with 7, G3 with 5, and the other things. And there should not be any repetition of labels. And the graceful labeling is defined like the edges will receive the labels, which is nothing but the difference of the labels at the end vertices of the edges. Let me take G1 and G2 dash. So the labels at the end vertices are 1 and 2. So the difference between these two will be 1. Similarly, when I take G1 and G3, so the absolute difference between the labels at the end vertices is 4 minus 1, which is 3. And similarly, they are labeled and all the edge labels are distinct. So when this condition is satisfied, then we call the graph as a graceful graph and the labeling as graceful labeling. Then comes odd graceful labeling. So here what we do, the vertices of the graphs are labeled using the integers 0, 1, 2, 3 up to 2q minus 1. Here again q represents the number of edges. And the induced function which induces the edge label will remain same, h of y minus h of z. And the resulting edge labels will be the odd integers from 1, 2, 3 up to 2q minus 1. So again, I am taking example of bystander. So this is an example. I don't want to explain this. It will take much time. Then even graceful. In even graceful labeling, we call the graph G as a even graceful labeling when the vertices of the graph are labeled with the 0, 1, 2, 3 up to 2q. And this induced function h of y minus h of z will give the labels to the edges, and the resulting edge labels will be distinct even integers 2, 4, 6 up to 2q. So 0 to 2q. So here we have 12 edges, 12 vertices, and number of edges will be 11. Therefore, when you look at the definition, the vertices are labeled from 0 to 2q. So we have 11 edges here, so you can label up to 22. So look at the labels of the vertices 0, 2, 4, 6, 8, 10, 12, 20, 18, 16, 14, 12. So I have used up to 20 only. And the resulting edge labels are distinct even numbers. Therefore, the extended duplicate graph of star admits even graceful labeling. And next comes odd even graceful labeling. So here, the vertices of the graph are labeled using the odd integers 1, 3, 5 up to 2q plus 1. And the induced function remains same, absolute value of phi of u minus phi of v. And the resulting edge labels will be distinct even integers 2, 4, 6 up to 2q. And here is an example for that. Then 1 modulo 3 graceful labeling. Actually, this concept of 1 modulo n graceful labeling was introduced by Ramachandran and a student a few years back. And we restrict this n to be 3, and we have defined 1 modulo 3 graceful labeling. So a graph G is said to be 1 modulo 3 graceful if there is a function phi from the vertex set of G to 0, 1, 3, 4, 6, 7 up to 3 times of q minus 1 and 3 times of q minus 1 plus 1 in such a way that phi is 1 to 1 and phi induces a bijection phi star from the edge set of G to 1, 4, 7, 10, etc. up to 3q minus 2. And here again, the induced function remains same, phi of a minus phi of b. And here is an example for this. So edge labels will be 1, 4, 7, 10, 13, 16, 19, 22, and 23. Then comes column graceful labeling. Consider a graph with P vertices and Q edges. The injective function H from V to 1, 2, 3 up to P is said to be a column graceful labeling. If the edge labels induced by this absolute value of H of I minus H of Z for each edge Y is are 1, 2, 3 up to Q. So here the vertices will be labeled from 1, 2, 3 up to P. P is the number of vertices and the edge labels will be 1, 2, 3 up to Q and Q is the number of edges. And the necessary condition for a graph to be a column graceful graph is P must be greater than or equal to Q plus 1. Only when this condition is satisfied, the graph will admit column graceful labeling. So now the extended duplicate graph of star graph admits column graceful labeling, but the duplicate graph of ladder graph does not admit column graceful labeling. So here is the reason. Then K graceful, and it is just an extension of graceful labeling. The difference is here the vertex labels are from 0, 1, 2, 3 up to Q plus K minus 1. And here the edge label will start from K, whereas in graceful labeling, it will start from 1. So in K graceful labeling, it will start from K. The remaining concepts will be same. So here is an example of 3 graceful, whereas here I have taken K as 3. So the edge label will start from 3, 3, 4, 5 up to 10. KD graceful labeling. So K is the starting number and D is the difference between the numbers. So a K graceful labeling is extended into KD graceful labeling by assigning the vertex labels from 0, 1, 2, 3 up to K plus Q minus 1 into D, and the induced mapping H star defined by same H star of Y Z is equal to absolute value of H of Y minus H of Z, which induces the edge labeling K, K plus D, K plus 2D up to K plus Q minus 1 into D. A graph is called a KD graceful if it admits KD graceful labeling. Now here I am taking the initial value of K as 3 and D as 2, and this is an example. It starts from 3, K value is 3 and D value is 3. So 3, 5, 7, 9, 11, 13, 15, 17 and 19. And accordingly, first we have to fix the vertex labels. Then from the induced functions, we will get the edge labels. Now, as I already told you, the Cordial labeling was introduced by Kahit as a weaker version of Harmonious and graceful labeling. So let me give a brief outline of Harmonious labeling. So here, let me tell you about Harmonious labeling: odd harmonious, even sequential harmonious, K odd sequential harmonious labeling, and K even sequential harmonious labeling. And this K odd sequential harmonious labeling and K even sequential harmonious labeling are recently defined. So what is an harmonious labeling? A graph G with Q edges is said to be harmonious if there exists an injective function H from the vertex set of G to the group of integers modulo Q, such that when each edge Y is assigned to the label H of Y plus H of Z mod Q, and the resulting edge labels must be distinct. So I think it's a huge example. Let me move on to the next one. So non-existence of harmonious labeling. So here also for duplicate graph, harmonious labeling exists, whereas for extended duplicate graph of star graph, the harmonious labeling does not exist. And odd harmonious labeling. A 1-to-1 map H from B to 0, 1 to up to 2Q minus 1 is said to be an odd harmonious labeling of a graph G with Q edges if the induced mapping H star of Y Z is equal to H of Y plus H of Z labels the edges of G with odd integers from 1 to 2Q minus 1 such that H star is a bijection. The thing is, everywhere when you see the conditions are very important. And here is an example for the existence of order harmonious labeling in extended duplicate graph of star graph, and this is the existence of harmonious labeling in ladder graph. Then even harmonious labeling. So here the vertices are labeled with 0, 1, 2, 3 up to 2Q, and this induced function will give labels to the edges as 0, 2, 4, 6 up to 2Q minus 2. And again, here is an example. I have taken a star graph and ladder graph. Even sequential harmonious labeling. I don't want to explain this. It's a huge one. Then K odd sequential harmonious labeling and corresponding examples, K even sequential harmonious labeling. Now comes the cordial labeling. Now I have listed out only few cordial labelings here. Cordial labeling, K cordial labeling, and the 3 cordial labeling is a special case of K cordial labeling limiting K to 3. And V cordial labeling, it is also called as cup cordial labeling. Some cordial labeling, even some cordial labeling, difference cordial labeling, remainder cordial labeling, product cordial labeling, signed product cordial labeling, prime cordial labeling, SD prime cordial labeling. Here S represents some, D represents the difference. 3 equitable prime cordial labeling, mean cordial labeling, and more, and many more cordial labelings are there. Now, what is a cordial labeling? A function H from B to 0, 1. It means the vertices of the graphs are labeled using only zeros and ones, is such that the difference between the number of vertices with the label 0 and 1 is at most 1. Is said to be cordial if each edge YZ is assigned the label H of Y minus H of Z. Now it is nothing but the induced function of graceful labeling. So that the number of edges labeled with 0 differs by at most 1 from the number of edges labeled with 1. A graph which admits cordial labeling is called a cordial graph. So let me give an example for this. So here it means we have to label the vertices in such a way that the difference between the number of vertices with the label 0 and the number of vertices with the label 1 will differ at most by 1. And then using this induced function, we will be assigning labels to the edges. And also the edge labels must satisfy the condition that the number of edges with the label 1 and number of edges with the label 0 will differ at most by 1. If these two conditions are satisfied, then such a labeling is called a cordial labeling. And for a simple example, I take, it is only a star graph. It's an extended duplicate graph of star graph. So here we have 10 vertices and 9 edges. Now, when you look at the vertex labels, let me count only the zeros. 1, 2, 3, 4, 5. So I have 5 zeros and 5 ones in vertex labels. So the first condition is satisfied. Now the edge labels are assigned using taking the absolute difference between the labels at the end vertices. So 1 minus 0 and 1 minus 1, 0, 1 minus 0, 1 again. Like that, when you count the number of zeros, here we have 4 zeros and 5 ones. So the second condition is also satisfied. Therefore, this graph is a cordial graph. Then K cordial graph. So let G be a graph with a vertex at V and the edges at E. A vertex labeling F from V of G to ZK, it is nothing but integer modulo K. Induces an edge labeling F star from E of G to set of integer modulo K, defined by F star of UV is equal to F of U plus F of U mod K for all edges UV in edge set. Then for I in Zk, let Ni of F is number of vertices with the label I, and here this Mi of F represents the number of edges with the label I. A labeling F of the graph G is called K cordial if the difference between the number of vertices having label I and J is at most 1. Similarly, the same condition for edges also. Now, fixing K as 3, we call this as 3 cordial labeling. An example of this. So here we take only 0, 1, 2. And in vertex labels, let me look at only this. It will be easy to understand. So here you count the zeros, 1, 2, 3, 4 zeros. There are 12 vertices, 4 zeros, and 1, 2, 3, 4 ones, and the rest will be 2. So the first condition is satisfied. So the number of vertices with 0, 1, 2 are all same. And when you look at the edge labels, let me count 0, 1, 2, 3 zeros are there, and 4 ones are there, and 3 twos are there. So here the condition is the number of edges having labels 0, 1, 2 will differ at most by 1. So here, when you consider the number of edges with zeros and 2, it is 3. Zeros and 1, it is maximum difference is 1. Similarly, between 1 and 2, it is again the maximum difference is 1. Therefore, this star graph, extended duplicate graph of star graph admits 3 cordial labeling. And this is the existence of the same in ladder graph. Then V cordial labeling, or sometimes it is called as cup cordial labeling. So a cup cordial labeling of the graph G with the vertex set V is a surjection, which is an onto function. Phi from V to the set 0, 1 such that the induced function phi star from E to 0, 1 defined by phi star of AB, here AB is edge, will receive the label 0 whenever phi of A is equal to phi of B is equal to 0. That is, this edge AB will receive 0 if the labels at the end vertices of the edge is 0 and 1 otherwise. So here is an example. It's a simple labeling. Then some cordial labeling. A binary vertex labeling of a graph G with induced edge labeling H star from E of G to 0, 1 defined by H star of Y Z is equal to H of Y plus H of Z mod 2 is called some cordial labeling if VHS is 0 minus VHS of 1. Absolute value is less than 1. That is, it means the number of vertices with the label 0 and 1 differ at most by 1. Similarly, here this means the number of edges with the label 0 and 1 will differ at most by 1. And here is an example. Then the sum cordial labeling is extended to even sum cordial labeling. Here, in sum cordial labeling, when both the vertex labels are 0, then the edge was assigned label 1. And here, when the sum of the edge vertex labels at the end of the edge is even, then we assign 1, otherwise 0. And here is an example for the even sum cordial labeling. And difference cordial labeling. So the vertex labels are from 1 to P, and the edge labels are assigned using this induced function. The condition remains same. The number of edges labeled with the 0 and the number of edges labeled with 1 differs at most by 1. So here is an example. And reminder cordial labeling. So let G be a PQ graph. It means graph is having P vertices and Q edges. And let phi from B to the set 1, 2, 3 up to P be an injective map. For each edge UV, assign the label R. What is this R? R is the remainder when phi of A is divided by phi of P, or phi of P is divided by phi of A, accordingly, which is greater. The function phi is called the remainder Cordial labeling if this number of edges labeled with the 0 and number of edges labeled with the 1 differ at most by 1. So here is an example. So here the vertices are labeled. Then now when you divide 2 by 1, remainder will be 0. When you divide 8 by 2, the remainder will be 0. When you divide 3 by 2, the remainder will be 1. When you divide 12 by 9, the remainder will be 1. And similarly, other edge labels are assigned. Then product Cordial labeling. Here in product Cordial labeling, the vertices are labeled with the zeros and 1 with the same condition that the number of vertices with the label 0 and 1 differ at most by 1. And the edge labels are nothing but the product of the labels at the end vertices. And such that the number of edges with the label 0, number of edges with the label 1 differ at most by 1. Then signed product Cordial labeling. Instead of 0 and 1, here we take -1 and +1, and the conditions remain same. Then comes prime Cordial labeling. A prime Cordial labeling of a graph G with vertex at B is a bijection H from B to 1 to B. It means the vertices of the graph are labeled from 1 to 3 up to the number of vertices, such that each edge YZ is assigned the label 1 whenever the GCD of the labels at the end vertices is 1 and 0 otherwise. So here is an example. And SD prime Cordial labeling. A bijection phi from B to set 1 to 3 up to P induces an edge labeling E of G to 0, 1 such that for each edge UV, the edge labels are like this. Phi of UV, that means this edge UV receives the label 1 when the GCD of sum and difference between the labels at the end vertices is equal to 1 and 0 otherwise. And moreover, the number of zeros and number of edges with the label 0 and 1 will differ at most by 1. So here is an example. I have taken path graph for this. And 3 equitable labeling. I think we are running short of time. So in mean labeling, we have mean labeling, odd mean labeling, even mean labeling, 1 modulo 3 mean labeling, scolum mean labeling, scolum difference mean labeling, scolum difference odd mean labeling, scolum difference even mean labeling, even vertex odd difference mean labeling, even vertex even difference mean labeling, and the even vertex odd scolum difference mean labeling and the even vertex even scolum difference mean labeling is also introduced very recently. And there are many more mean labelings where you can work. So let me just rush through this. Now the super duplicate graph, which was introduced by Professor Janakiraman of NIT Tiruchirappalli very recently. And after one paper, I think nobody has worked on this as of my knowledge is concerned. So if anybody wants to do a good research, you can consider super duplicate graph and you can work on this, you will get good results. Now even 3 equitable prime Cordial labeling, which is an extension of prime Cordial labeling, and even very few work has been carried out on 3 equitable prime Cordial labeling. So scholars can work on this. There are a lot of problems exist on 3 equitable prime Cordial labeling. Even mean Cordial labeling, but on mean Cordial labeling, many work has been carried out. Now, triplicate graph. Just I want to give a brief introduction of this. Actually, this was introduced by Professor Thirisangu and Bala of SIVT College, Chennai. And instead of defining a triplicate graph, they have defined only a triplicate graph of path graph. And if anybody wish to define a triplicate graph taking this as a base paper, you can define a triplicate graph and you can generalize, and you can even study the characteristics of a triplicate graph. Then applications of graph labeling, and most of you will be knowing graph labeling has a wide range of applications in various fields of science, engineering, technology, all that. Now, myself with my candidate, we did an application on cryptography, encryption and decryption of integers, signals, using anti-magic labeling and magic labeling. And we have received actually applied for patent for that. We are to get it. Now, thank you all for your patient listening. Any queries? Any queries, any doubts? Anything extra you require?
Dear participants, if you have any queries, you can post on your chat box.
I think there are no questions.
Yes, sir, your presentation was questionless. I think that's the reason. Yes.
Okay. Thank you all for your patience listening. Anita madam, shall I quit?
Yeah. Sir, please wait for a moment, sir, because we have photo session.
Okay, okay.
What we know is a handful. What we don't know is the size of the world. Thank you, sir, for your presentation about the different labelings, odd even grace labeling, scolum grace labeling, K graceful labeling, odd humanist labeling, cordial labeling, K cordial labeling, V cordial labeling, and so on. Even I couldn't take a breath for saying the names of different labelings, sir. Really, your presentation was more informative, very clear, and graceful too, sir. Now, I invite Mrs. Nandini, Assistant Professor, Department of Mathematics, to present vote of thanks.
Thank you, ma'am. Can I audible, ma'am?
Yes, audible, pa.
Ma'am, may I audible?
Yes, audible, pa. Nandini ma'am, you are audible, ma'am. Please continue.
Nandini ma'am, you are audible, ma'am. You can continue.
Nandini madam, please unmute your mic and then speak, madam.
Nandini ma'am, please unmute your audio, please.
Ma'am, mute எடுங்க. நந்தினி ma'am,
Nandini ma'am.
பேசுங்க இப்ப.
Yes, you can speak now.
Yes, ma'am. Ma'am, the host will not allow coming, ma'am.
Yes,
Okay,
yes.
ma'am. Shall I start, ma'am? Okay. Mathematics reveals its secrets only to those who approach it with pure love. Good evening to everyone present here. On behalf of Department of Mathematics, New Prince Shri Bhavani College of Engineering and Technology, I extend my sincere gratitude as we conclude the first day of our 5-day faculty development program on innovative applications of mathematics in real-world challenges. I convey my deep gratitude to Dr. P. Vijayakumar, COE and Professor of Mathematics, GIET University, Gunpur, Odisha, for today's inspiring and thought-provoking session. Your practical insights have laid a strong foundation for the rest of the program. I wholeheartedly thank our respected chairman and vice chairman for their constant encouragement and visionary leadership, which make impactful academic events like this possible. I offer my warmest gratitude to Dr. Saravanan, principal of our institution, for his continual guidance and motivation to explore innovative academic initiatives. I gratefully acknowledge the support of our director for fostering an environment that encourages knowledge sharing programs such as this FDP. I wish to place on record my sincere thanks to Dr. Sivagami, Head of the Department of Science and Humanities, for her valuable guidance and encouragement throughout the planning and execution of this event. It gives me immense pleasure to thank Dr. G. Puspalakshmi, our dedicated coordinator, for his meticulous planning and tireless efforts that ensured the smooth conduct of today's session. I warmly kept every segment perfectly timed.
Nandini ma'am, have you completed? Dear participants, please all of you on your video for your photo session. Please wait for some more sessions.
Anita madam, there is a
Yes.
print screen option. You can use that print screen so that picture will be very clear.
Yes, sir. Yes, sir. Actually, I have to paste in some other word, no, sir.
Okay,
That's why.
okay.
Yes, sir. Yes, sir. Sir. Sir, actually, I'm sorry for it. There is some technical problem only in my computer, so I couldn't do it properly, the full session. So sorry for it. So tomorrow we'll rectify everything. And we have posted the feedback link in the chat box. You can give your feedback for today's session. Sir, thank you, sir. Thank you for your presentation. Thank you so much. Dear participants, thank you for your patience to attend the session. So tomorrow we'll meet again in the same time. Thank you one and all. Have a good day. Good night.
Thank you all.
Thank you, sir. Thank you.
Concluded.